All right, so welcome to Math 408, L functions and sphere packing. Oh, except this is supposed to be lecture 34, so I will switch that and fix that later. So we are at the home stretch of the semesters. We've got 3 classes left and chances to show a little bit about how things go. So one of the things I want to do is I want to get to how do we do better with sphere packing in high dimensions. And it turns out that we can do well in some dimensions, but not all high dimensions. Well, we've done dimensions 1 and 2 in great detail already, but we haven't done dimension 3. And so before we go into the higher dimensions, it's worth doing at least one lecture talking a little bit about what is going on in 3 dimensions. If you want to know more, there's going to be a lot of links you can read. I'm also happy to give you the chapter that is devoted to this on my book. This is one of the most monumental math achievements from the last century. So to put things a little bit in perspective, it's the Kepler conjecture goes back to Johannes Kepler, goes back to a paper he wrote in 1611. And so the paper is on the 6-cornered snowflake. What is wonderful is with a little bit of research on the web, it took me a while, but I was able to find a PDF version of the Kepler paper. The standards at Williams, I think, have declined since our founding. I do not believe everybody knows Latin anymore. I think in the last few years, I've only had one student who I would trust with the Latin version of this paper. The version I found on the web has both the Latin and the English on opposite pages so that you can read either one. So Kepler conjectured on the optimal way to pack spheres in 1611. The proof was announced in 1998. And there was a lot of interesting dispute about his proof. To put things in perspective, hopefully everybody has heard of Fermat's last theorem, stated in 1637. Fermat scribbled it in his copy of Diophantus's book. The proofs were announced, finally with all the corrections and whatnot, in 1995. So the Kepler conjecture is a little bit older than Fermat and resisted analysis a little bit longer. And so just a couple of little images. Essentially, the Kepler conjecture says you do things exactly as you would expect. You start off with a hexagonal packing, and then you put the balls in the next level indented as you would expect. Okay, so the question is, how do you prove this? What are the ingredients? So I'm going to just give you a couple of snapshots from the chapter that I wrote with my students on this a few years ago. I do not want to go into all of the technical details. It is a monumental task to really get into the weeds on this. I want to do the 30,000-foot overview of the subject because this will allow me to introduce another wonderful topic, operations research and linear programming. And again, one of the goals of this course is to see where the math goes, to see how things are done. The great challenge in Kepler's proof is that there was a huge computational component. And the mathematics community was not really set up to handle proofs like that. And this becomes an interesting question of what do you consider a proof? How much detail do you need? And as a referee, what is your job when you have something like this? So I remember when I was in grad school, the great John Conway was wonderful about talking to students. And I remember having a conversation with him about what is the job of the referee. And I felt my job was to check line by line, word by word, symbol by symbol. And what he said is, well, that's wonderful. If you do that, you're never going to have time to do anything else. And it is a difficult job balancing how much do you do and how much do you trust the author and the scientific community, the people who truly need the results, who will be looking at things in great detail. Did I share the story of the PhD that failed at Princeton during the defense?
No.
All right, so somebody was defending their thesis, and either Mather or Milner in the audience said, well, what about the following? It satisfies your conditions, but not your conclusion. And the grad student is trying to explain why it's not a contradiction, but is having trouble and is stumbling, and eventually becomes quite clear to the advisor that the graduate student has no idea how to answer the question. So the advisor steps in to help, and after a while, the advisor too is stumped. And it turns out a counterexample to the thesis was developed on the spot. It turns out, they did a little bit of work on this because obviously this is very important. The student was using a paper that was published in the top journal that was wrong. What do you do if you're Princeton? The student worked in good faith. The student used the literature. The advisor thought the paper was fine. Does the student get a PhD?
Yes, and then you blame the referee.
All right, so I have one vote for yes. Any other votes?
Vote yes.
I'll second that.
I vote yes.
The
Okay.
easier we make it to get a math PhD, the better.
Right.
I think yes, because like it's on the people who accept it in the top journal, right? Like for like letting through something that's wrong.
But
So the
maybe you
answer-
could say that the person doing the thesis should have realized it was wrong.
And that's the point, is they should have realized it. If there was a result that was so central to their thesis, their job is to know it. Now, if you truly enforce such a standard, this means you can't accept anything. You have to prove everything. In my thesis, I actually use Wiles's proof of Fermat's last theorem. I use the modularity conjecture, the Taniyama-Shimura-Vey. I'm in enough trouble that I'm just going to throw every name there and try to appease all groups. He did not get his thesis. His thesis was wrong. Now, what Princeton did is they said, look, this is, an exceptional situation. We will give you funding to stay for another year and fix your thesis. And so it was very good that this happened early in the person's career. They fixed the thesis, they fixed the paper that was published. It turns out that paper was missing a condition. And when you put in that condition, it then eliminates the counterexample. It makes the thesis result a little bit more restrictive, but it also makes it correct. So just because you have a human paper does not mean that the paper that has been read by humans line by line has been correctly read. There are very delicate arguments, and it is extremely easy to make mistakes. If you talk to almost any professor, they can tell you the story of the day their thesis died. Mine was about a week or two before I defended, when I realized I accidentally assumed something in some of the calculations, and all of a sudden, my result was a lot less general than I had thought. And how do you deal with something like that? So when Hales finally announced a proof of the Kepler conjecture, a tremendous amount of it revolved around computations done by computers. And the first real instance of this in mathematics was the four-color proof, going back a few decades earlier, where if you have nice countries in the world, you cannot come up with a configuration where you need more than 4 colors. Which state in the United States of America would be bad for the four-color theorem, for those of you who know it?
Wait,
Michigan?
Michigan, exactly. Yeah. And I love this as an Ohio State fan, being able to talk about the evils of Michigan. Why is Michigan so horrible? Just one of the many reasons.
Not connected.
It's not connected. So you have the Upper Peninsula in Michigan, which is not connected. And so if you have stuff like that, well, if you have disconnected parts of states, you can clearly have a configuration where you need more than 4 colors. University of Michigan, however, is phenomenal. And I am in fact wearing a Michigan Math Corps shirt in honor of the great program that they do. So there's a lot of difficulties in Hales's proof. And
But Michigan doesn't actually break it, right? Because it's only touching 3 other states.
Right, so you can do it with Michigan. It's still okay because of how things go. But it could be a problem if you had a lot of isolated parts of states. So the first issue, and again, I'm trying to just give the really high-level overview, is coming up with a rigorous notion of what we mean by density. And we've seen a couple of times in the semester, for instance, when we talked about dimension, that it can take a while to come up with a good definition that is mathematically tractable. The next is, we have to be very careful about local conditions, because if you're looking about density and you have density defined in the limit, well, if you change things locally in just one small spot, it's not going to affect any of the limits. It's just something to be aware of. The third difficulty is that there are actually infinitely many, in fact, uncountably many dense packings that are in some sense different from each other. The trivial way is just to put down the different levels in slightly different ways to give you a little bit more freedom. So we have to be a little bit careful about what we mean as we're going through the possibilities. One of the other ingredients that arises is something that we talked about earlier in the semester is a Voronoi cell. It's going to be the set of all points in space that are closer to it than to any other. Okay. And then here is the kicker, is that the optimization problem is essentially infinite dimensional. Infinite dimensional problems are a pain. And so Hales did a tremendous amount of work to get around this. And he was able to do it in such a way that he was able to convert it to a finite dimensional problem with what was called a local density inequality approach. One of the last ingredients that I want to mention is interval arithmetic. The way a lot of the argument worked is we know the density of the hexagonal sphere packing. So what we want to do is we want to show that any other packing that's not essentially equivalent to it has a lower density. Or if you want, that nothing has a better density. One way to do this is to just look at some of the other packings and try to estimate, well, what is their density? We don't have to compute it perfectly. We just have to compute it well enough to show that it is less than the hexagonal packing. And so this is where the idea of interval arithmetic comes from. So if you have a calculation and you have some uncertainty, what you can say is, well, look, my value lives between A1 and A2. And as I go to the next stage of the process, I look and I see, where does this interval map? And then maybe it maps to, let's call it A1, B1, now it maps to A2, B2. And then I look at what happens when I map that in the next iteration, and I'll go to A3, B3. And again, it's sometimes not enough to look at just what happens to the endpoints. It's nicest if that happens if you have a monotonic function. But if your function is not monotonic, then it could be a little bit more work to figure out how the interval is mapped. But the idea is that every moment in time, you know your answer lies in a certain interval, and you just have to make sure at the end of the day that your interval is below the hexagonal density. What would often happen is when you try to do this in practice, you would get a value where you believe it's below the hexagonal, but the upper bound is just ever so slightly above. And what that means is you have to do more detailed work. All right, so the last thing, and the really interesting part, at least for me, that came into play was the linear programming bounds. And this is the part where the computers played the greatest role. And so they reduced the problem to a finite dimensional problem with 150 variables. Now, for us, that's terrible, but for computers, the computers can do this. And so they used it to solve a huge number of linear programming problems. A typical one had between 100 and 200 variables and 1,000 to 2,000 constraints. There were 100,000 such problems that entered into the proof. So you can imagine the nightmare that the refereeing committee has when this arrives. How do you make sure that every single case is correct? How do you make sure that it's exhaustive, that no cases were missed? And so there was a huge let's say controversy in terms of what kind of acceptance do we give this proof. And this led Hales to changing his research interests, and he has worked on formal proof systems where the computer can generate a proof certificate. And so there is now a formal proof certificate of the Kepler conjecture, as well as a variety of other problems. And this is an absolutely amazing development in mathematics. It is interesting to think of what is proof writing going to be like in the future. There have been great changes in the level of rigor over the centuries. But, for the most part, there hasn't been much of a change recently. The difficulty now is we are getting into very technical subjects with a tremendous amount of material, so much so that it is not always possible for everybody on the paper to have, read and grokked and mastered everything. And so can you somehow convert what you're doing to something that could be fed into a computer where the computer can go through and check? And then, of course, the question becomes, well, what is the role of the mathematician going to be in the future? How much is the mathematician going to become almost a computer programmer? All right. So what I want to do is talk a little bit about what is linear programming, because this is one of the key ingredients in the Keplers proof. If you then want to know more after this lecture, you should be poised to read that. I know at least 2 of you have seen these lectures, so please, if you've seen these lectures, do not volunteer. So this is one of my favorite problems to illustrate the ideas of linear programming or operations research. The goal is not just to solve problems, but to solve problems in efficient ways. If I want to calculate what is the best solution, if it's a finite problem, I only have finitely many things to investigate, then one solution is to just go through brute force everything. In practice, this is useless because it will take too long to terminate in a reasonable amount of time. For example, if you own American Airlines, and let's say this is before the pandemic when we have lots of flights, and you want to figure out what is the optimal configuration, what is the optimal schedule for you to fly, if it takes 30 years for the program to run, that's effectively useless. You can't wait 30 years for a schedule. So here's one of my favorite problems. Due to budget cutbacks, we can only afford a 5x5 chessboard, and we want to place 5 queens on the board in such a way that 3 pawns can be safely placed. And you can consider the more general question of, if you have an n by n board and you're placing queens, how many pawns can be safely placed? What's the maximum number? And it turns out this is a very hard problem as the size of the board increases, and we really don't know too much about how this function grows. We can prove some general statements such that in the limit, we have some idea of what percent of the board will be covered, even in the most generous arrangement of queens to help us as much. But anyways, right now, let's consider just the 5x5 board. We have 5 queens. We want to put them in such a way that we can place 3 pawns. And I've initially put a queen in the center square. Do you think this is a good idea or a bad idea?
Bad.
Okay, why is this a bad idea?
Because the queen in the center of the board covers the most squares.
Well, but maybe that's not a bad idea. Maybe I put the queen there and I put the other 4 in the 4 corners. And if I put them in the 4 corners, they're going to be hitting a lot of squares in common.
Yeah, but if you put them in the 4 corners, you still can't place 3 pawns.
Right, how many pawns can you place if you put them in the 4 corners?
0.
0.
So it's actually terrible. Okay. So, but maybe there's a better way to put down some of the other queens with a queen in the center. My feeling is a queen in the center is probably a bad way to start. Any thoughts about how we should explore the possibilities efficiently?
Seems that you would want to have them grouped right next to each other.
Okay, so it seems like you would want them to be close to each other because that way they can interfere with each other. So that's a good feature that we should be looking for. So maybe when we put down a queen, maybe the next queen has to be touching it. What else can you do to help me? So how many places do you have for the first queen?
25.
Okay, why 25?
5 times 5.
Oh, 5 times 5, 25.
We should try to reduce it based on symmetry, though. Like, if it's symmetrical with another arrangement, we should just treat it as the same.
Okay,
Yeah,
good. So,
that's like what? 25 over 4? 8.
so this is like tic-tac-toe. Did we talk about tic-tac-toe in this class?
No.
So how many opening moves are there in tic-tac-toe? Up to symmetry.
3.
3.
You can go in a corner, in a middle, or the center. And it's the same thing here. By symmetry, there's only 6 possible opening moves. You know, the 4 corners, the 8 squares next to corners, the 4 squares next to those, then these, then these, then these. And so you only have 6 possibilities. And so one way to attack the problem is when we put down the first queen, there's only 6 possibilities, not 25. Okay, this helps. Another way to look at it is there's 25, choose 5 ways to choose 5 squares from the board. And we could try to do something such that, you know, if I now choose the corner as my first piece, then I can start to think about where the second one might be. And all I would have to care about is the main diagonal here and the stuff above. So that would cut down in half where my next piece can go. And if I don't have something on the corner, you know, I might as well assume if there's something on the corner, it's the first piece. So this is one way to attack the problem. And this will cut down a little bit on the number of possibilities. Instead of 25 times 24 times 23 times 22 times 21, it's now 6 for the first one. And even if we don't do anything better, you know, 24, 23, 22, 21, we've still saved a factor of 4. Can we do better than this? So, you know, again, a factor of 4 is nothing to sneeze at, but we want something that's going to scale well. You know, as we get to a higher and higher problem, I want something that's a lot better than just a factor of 4.
Oh my god.
Any thoughts? And the hint is, it is related to something we have seen involving Fourier analysis.
Poisson summation.
Poisson summation. Yes, that is the answer. So how does Poisson summation help us here? It's clearly not going to be the standard Poisson summation. It's got to be something related to the idea of Poisson summation. So what is the idea of Poisson summation? Can someone describe what Poisson summation does? So what does Poisson summation do? So somebody tell me what the Poisson summation formula is.
It turns an infinite sum into a different infinite sum based on its.
Good. It turns one infinite sum into another infinite sum, and the hope is that new infinite sum will be easier to work with. So we want to adopt a new perspective. Rather than trying to place 5 queens so that 3 pawns are safe, is there a related problem we could attack?
Can you just place the 3 pawns and then place the 5 queens after?
Yes. And you could either do it that way, or you could place 3 queens so that 5 pawns are safe, and then change the queens to pawns. Either way works. The whole idea is to do a related problem that is easier. And so now, rather than looping on 5 objects, we're looping on 3 objects. There is a little bit of a trade-off in that we don't know necessarily how many pawns we can safely place. So, you know, if we try to place 4 pawns on a 5x5 board with 5 queens, there's no way to do that. So if you do it this way, you might have the trade-off of, we first try placing 2 pawns, we see that we can do it, we try 3 pawns, we see we can do it, we try to move up to 4 pawns, and then we see we're stuck. But it's still valuable, and it's still worth trying. And so this is called duality. Instead of looking at the problem that you were given, it's looking at a related problem. And frequently that related problem is just better to look at computationally. And this is one of the big themes of the class, that depending on what information you have, sometimes it's better to look at one thing than another. All right, so I want to give you the canonical linear programming problem. And so before I describe the definition, I'll look at the stuff a little bit lower. Where have you seen canonical before? Well, you've seen it in solving polynomials. You're writing a polynomial as quadratic as ax squared plus bx plus c equals 0, and using the quadratic formula. I have read math history books where they did not like writing all polynomials in this form, is they would split things up based on only having positive quantities. So if you had 3x squared minus x plus 5, they would do 3x squared plus 5 equals x. And they would be interpreting it as you have 2 quantities. This represents an area or volume or something like that. And we want the perimeter of this plus the area of this equals the volume of this, or something like that. And they would not want negative numbers. It's a lot more work. You now have to start having different formulas and different cases for everything. It's nice if you can say, look, whatever you give me, I'm going to just convert into a canonical form. And then once I have this canonical form, that's going to just tell me how to approach things. And so here, the canonical form of a linear programming problem is a generalization of linear algebra. So if you look at the last bullet point, linear algebra is concerned with solving ax equals b. And we developed lots of different techniques to solve this, to solve it efficiently. Typically, in a linear algebra class, what can you say about the matrix A? So if you're taking a first course in linear algebra, what is typically going to be true about your matrix A?
Probably invertible.
Probably invertible. It's almost surely going to be a square matrix. It's invertible, so you then get ax equals b, so you get x equals a inverse b, and it all comes down to, can you calculate a inverse? In a situation like this, it's not that exciting. It's a lot more exciting if you have an underdetermined system. So you have more variables than more variables than equations. And when you have more variables than equations, it means you have more than one possible solution. And if you have more than one possible solution, you now have the possibility of saying, which of these solutions is best? Which of these solutions has a property that I truly care about more than anything else? So rather than just solving a problem, you can now try to solve a problem with some additional hopes that I not only want to solve this problem, but I want my solution to be really good in this regard. And so we generalize this a little bit further. And so the way canonical linear programming works is we assume our variables are non-negative. We assume they satisfy some linear constraints, ax equals b. And typically we will assume that it's an underdetermined system, because if it's overdetermined, it's not exciting. And then the goal is to minimize a linear function of the variables. So c1x1 plus ... cnxn. So there is a tremendous literature on problems like this and why these aren't big assumptions. Which do you think is the big assumption? Minimizing versus maximizing, or that the variables are non-negative?
Probably minimizing versus maximizing.
Okay, so why do you think that's a worse assumption? Or more restrictive?
Or restrictive. Well, if you have a negative entry in some matrix, you can just keep adding to that row, and you're not really changing much of the matrix. You just multiply it by a constant.
So actually, negative is not so bad. So if instead of minimizing, if we want to maximize, all we do is we replace this function with negative C transpose X. And so if we replace it with negative C transpose X, then minimizing that is the same as maximizing the original function. So it's actually not that hard to go from minimizing to maximizing. For the variables being non-negative, there are games that you can play as well, and it turns out that that's not really too restrictive of a condition. In many problems, it's physically represented by conditions that you would want to impose. You know, if you're talking about how much food you consume, what should be true about the amount of food you consume?
It's a lot.
Okay, it's a lot.
It's non-negative.
It's non-negative. You know, you should not have the option of regurgitating food and being paid for that. You know, one of the first problems that this solved was the diet problem of what meal will give you all the nutrients you need at the cheapest cost. And in fact, when I was teaching this class at Williams for the first time, one of the groups did a project on this, and they actually went to one of the local supermarkets websites and downloaded all the information about all the products that you could buy and came up with the cheapest possible diet that would meet the US recommended daily allowances. And then they actually bought the material and brought it in for me to eat. And I was so grateful that I was on medication for something at the time and could say, I don't think I can risk eating this. That diet would keep you alive. It would also taste disgusting. And in fact, in the original work solving this, there was some conditions that were left out about some of the foods, which led to some very interesting possible solutions. So this is one of the reasons why the subject works as well as it does. So there's something called the dual problem. So, you know, given the problem, you know, ax equals b and the x's are non-negative and you want to minimize something, there's a related problem where, you know, you have the same matrix A, you have the same vectors C and B, but they're in slightly different roles. And the dual problem is to try to maximize y transpose B subject to y transpose A is less equal to C transpose. And the reason this is so valuable is because of the following lemma, that if you have a feasible solution to the original problem and a feasible solution to the dual problem, then this dot product involving the dual solution is at most this dot product for the feasible, I mean for the original. And if equality holds, then your x hat is optimal for the original problem. So what's nice about this, what's wonderful about this, what's amazing about this is you can tell how close you must be to the true solution. If you have a feasible solution for the dual problem and you have any feasible solution to the original problem, you know the optimal can't be too much better than where you are. It can't be better than this. And if they happen to be equal, then you know you've reached an optimal. And so a lot of times we're in the remarkable situation where we don't necessarily know what the best solution is, but we know that we are missing by at most 0.5%. And for a lot of problems, being off by 0.5% is not too bad. And so as you're going through Hale's argument, as he's trying to prove things, he doesn't have to find the exact values of certain things when he's optimizing these linear programs. He just needs to know how close am I. And that is a phenomenal world shift. That rather than solving the problem exactly, he just has to set things up enough to know, hey, this configuration will not be able to yield a bound, a density better than blah. And blah is below what the hexagonal packing does. Therefore, I can eliminate this case. And by doing this, he can eliminate a tremendous amount of cases very quickly. And then there are some cases where he can't eliminate. And then what that means is then you have to go into more detail just for those cases. So again, this is a real paradigm shift from a lot of the standard math classes where we are no longer trying to solve a problem exactly, we are trying to get close enough. The first time I actually used this professionally, I was helping some professors of marketing on a problem for the movie industry in terms of trying to figure out what movies to show on what screens at what time. And back then, the movie theater was very concerned about making sure that they made it to the papers in time to have the schedules published in the papers. And so we only had 2 to 4 hours to run our program. And so the goal was, what is the best solution we can get within 2 to 4 hours? And when you consider that in the real world, you're not going to know all of the values of your parameters, it's not horrible to be doing some approximations like this. So just explicitly so you could see an example of a problem, here's the diet problem. And we'll do the simpler version when you only have 2 foods, and each food has 2 nutrients. And you need a certain amount of each nutrient to stay alive. You need to get at least B1 units of the first and at least B2 units of the second. And so we'll assume food 1 gets A11 of nutrient 1 and A12 of nutrient 2. So this will be A11x1 plus A12x2 is greater than or equal to B1. And similarly for the second. And then the goal is to minimize the cost of your diet, subject to you eat non-negative amounts and you receive enough nutrients to stay alive. You could, of course, adjust things, and you could say, well, maybe there could be a problem if we eat too much of a food. You could absolutely add that as a constraint. And if you look at some of the experiments they do on mice, where they give the mice like 10,000 times the human dosage of something, and what a surprise, something happens to the mouse, you know, maybe there is a danger if we eat too much of something. In terms of how you solve it, the theory is beautiful. And if you go back to multivariable calculus, you know, we find interior solutions, and then we find boundary solutions. And what's nice here is, you know, these lines are the plots of the lines over here. You know, A11x1 plus A12x2 equals B1, A21x1 plus A22x2 equals B2. And then because we have to be greater than or equal to 0, you have to be above each of these lines. So you have this nice polygonal region, and we live inside. And then these lines here are of constant cost. And so if you're at any interior point, if you just flow towards the boundary, your cost goes down. So in linear programming, the optimal solutions live on the boundary. That's wonderful. So now we only have to check the boundary. Well, there's still infinitely many points on the boundary, so you might be a little bit concerned, but it's a good infinity because if we hit the boundary over here, well, we can still keep flowing on the boundary. We're going to keep flowing until we hit a point of intersection. And there's only finitely many points of intersection. Now, as your problem becomes more and more complicated, as is true in the Hales problem, the geometry becomes a nightmare. And you have a tremendous number of boundary points. It's a finite number, but it's a tremendously large finite number. Here, there's only 3 points. And so we just have to check these 3 points and see which one is best. And so in this particular problem, the way the costs are, this would be the one that would give you the optimal diet. So we actually have nice ways in problems like this to find the optimal solution. So as was mentioned, this is very similar to the Poisson summation formula, where we can often take, here's an example with the Gaussian. Here is a sum, infinitely many terms, and it's slowly decaying. If capital N is huge, all the way up to n is less than square root of big N, the terms are going to be of size 1, and they're going to matter. On the other side over here, when big N is huge, if little n is 0, you get 1. And then once little n equals 1, you have e to the negative pi times capital N is tremendously small. So the right-hand side is extremely well approximated by just one term. Okay, unfortunately, and this is an issue we've seen before in the class, it is not the case that everything we want to do involves just real variables. They are often integer valued restrictions. And so I have pasted links to 2 of my favorite scenes. One is from Seinfeld, and one is from the movie Father the Bride. The Seinfeld one is when Kramer decides that he wants to be able to buy just part of a can of Coke from Jerry. And Jerry has a different opinion on that. It is tremendously challenging to handle integer constraints. And we saw that when we talked about the knapsack problem. We saw that when we talked about the breaking a number n into lots of different pieces. And so it turns out we can handle a bunch of things with integer programming. And so here we want to allow some of the variables to be discrete. Well, what do we need? Well, one of the things I want is any quantity under consideration I want to be bounded, and I want to assume that there's a fixed smallest unit, which everything else is an integral multiple. These are not tremendous assumptions. You can weaken them, but it leaves a bunch of natural things you can do. I'm going to just show one example. You are welcome to look at it later if you're interested. Consider some quantity A that lives between minus NA and positive NA. And we want a new variable ZA that will be 1 if it's positive and 0 otherwise. And there is a way to do this at a cost of adding one variable that's either 0, 1 and 2 constraints. So the whole point of this is to just show that we can actually create a detector variable that will detect whether or not our quantity is positive or whether or not it's greater than or less than any fixed bound. With a little bit more work, in addition to the threshold, logical operations like and, if, or, exclusive or, inclusive or, they can all be done. We can truncate. We can replace our value with saying, look, take the regular value, but if it's less than 0, then just make it 0. And this is extremely important, for instance, when you do things with logarithms. We can't take the logarithm of a negative number, and so we often look at the log plus, which returns different things if you try to put in 0 or a negative number. We can deal with maximum and minimum. We can deal with absolute values. We can handle all of these within the confines of linear programming. So when Hales is trying to use linear programming to solve these problems, it's not just confined to the functions, y equals ax plus b. This is similar to the method of least squares or linear regression. If you've seen stuff like this before, that by doing the log change of variables, you can linearize a lot of things that aren't linear. The problem is there is a tremendous, I seem to like that word today, cost to doing this. Linear programming, when you do it with real variables, actually runs quickly. When you do it with integer variables, it no longer runs quickly. It actually is a very challenging problem. For my computer scientists in the class, what is the technical term?
For constraints?
No, for the type of problems like linear programming is.
I don't know. Is this an
NP hard?
NP?
It's NP high. It's equivalent to like the traveling salesman.
Yeah.
So you're basically screwed if you want an exact solution. As an aside, a lot of times you can try to find more efficient ways to code things or attack things. Here's one of my favorite examples, solving Sudoku. So my mother and my wife both disgusted might be too strong of a word, but maybe disappointed that the way I chose to solve Sudokus was to train my computer to solve Sudokus. How many conditions do you have to check to see if a solution is right?
You have to check every row, column, and like group of
Box.
9. Like every
Okay,
box,
good.
yeah.
So how do you check a row? What do you have to check?
That it sums to.
Well,
It has each number Zagger wants.
That it has each number. So for each row, you have to check, is there a 1? Is there a 2? Is there a 3? That's 9 checks for each row, 9 for each column, 9 for each block. That's a lot. Here's a faster way to do this. It doesn't matter if we use the numbers 1 through 9, or if we use fruits and vegetables, baseball teams. Let's use powers of 10. 1, 10, 100, 1,000, all the way up to 10 to the 8. Why is this better? Now, if you look at a correct row will have the sum 111,111,111. Any other row choice, where you don't use each number once and only once, will have a different sum. So all we have to do now is check to see, do we have that sum? If you use the numbers 1 through 9, unfortunately, 1 through 9, what would that sum to? You can tell me quickly.
45.
45. And plus,
You could just have 9 5s or something.
you could have 9 5s. You can replace the 1 and the 9 with another 2 and an 8. So there's many different ways to get the same sum. This is a really nice trick. There's a lot of tricks like this in programming. What I want to end with is just a little bit of a talk about how you might try to solve problems like this. One of the approaches, for the traveling salesman problem is, you have a bunch of cities. You will assume you can get from any city to any other city, and you want to take the route that gets you through everything in the shortest time, or the least distance. And the greedy algorithm is often an okay way to go. And what you do is at every moment in time, you do what is locally best. And so over here, what's locally best is to go from A to here, and locally best to go here to here to here. I guess the way it's being drawn here, maybe I should, I need to end at B. So I then have to go here and then go all the way back to B. Whereas over here, I make a decision that is not locally best, but is going to help my route. And this simple example shows you how difficult it can be to come up with optimal solutions for problems like this. And so what I want to end with is a nice application of this thinking, and it will prove one of the most useful interfaces in all of mathematics. So I have actually met both Timothy Pennings and his dog. His dog was named Elvis. And he wrote 2 papers on whether or not his dog knows calculus, or more generally, does his dog know bifurcations. And so the problem is, you have a little bit of a beach over here, and you have an ocean, which has an incredibly nice boundary with the beach. You have some dog in the water, and you throw a stick. And the dog is going to try to get to the stick as fast as possible. What route will the dog take to get to the stick?
Something that's like somewhat diagonal through the water flow.
Yeah, so the most natural thing is the dog will just swim directly to the stick. And that is the greedy algorithm solution. At every moment in time, you do what is locally best. Can anybody think of another way the dog might go?
Against the current, so that when the current is factored in, you end up at the stick.
Okay, so we will assume that we have gone to the physics store that sells the frictionless planes, the massless pulleys, and we have the currentless ocean. There is another path the dog could take.
A very curvy one.
Okay, but a curvy one should be worse than the straight line path.
Yes.
There is a path that's better.
You could get out of the water.
Yes. So the dog could run to the land, swim to the land, and then run on land, and then swim back to the stick. And again, initially this looks like a foolish idea, because if you're doing this, you're not doing what's locally best, but you're paying a small price in the beginning for much larger gain later. And the idea is the dog will run faster on land than the dog can swim in the water, and so it's worth it for the dog. And what's beautiful about this is it actually gives a proof of the arithmetic mean geometric mean. So imagine you are x1 units, the dog is x1 units from the ocean, and then x2 units from the ocean is where the stick is, and there's some distance over here. There's going to be some magical distance where the direct path like this is going to be the same as the path like this. Anybody know what speed I'm assuming the dog has on land?
Very fast, I guess.
Yeah, I might even be assuming an infinite speed on land.
That's maybe a little too fast.
It might be a little bit too fast, but in a situation like that, when you have this critical threshold, in a situation like that, the dog would want to get to land as fast as possible. If the dog has a finite speed on land, you would go at an angle. So I believe, yes, that in the limit, as the dog runs infinitely fast on land, this will lead to a proof of the arithmetic mean geometric mean. And so it's worth staring at this for a little bit and seeing what it is saying. So this is the quick one class high level overview of what Hales did to solve the Kepler conjecture, to solve sphere packing in 3 dimensions. And this is a complete solution in 3 dimensions. The key ingredient is converting a infinite dimensional linear programming problem down to a finite dimensional one, we have great local control over what's going on. And in using interval arithmetic, we keep looking at all of the different cases. And we do the analysis well enough not to solve what the best solution is, but to use the duality to get close enough to what the solution says. Look, I haven't solved it, but I know the best solution is no more than 0.03% more than where I am. And even if I could gain all of that, it would not be enough to push me all the way to something better. Okay. Any questions